Hi, I'm Luis Gustavo Nardi, an executive committee member of RoboCup Rescue Simulation, together with Farshid Faraj. Today I will give you a brief overview of what RoboCup Rescue Simulation is, and a little perspective of how you can use the tools developed in this working group for post-disaster planning. But before we start discussing what rescue simulation is, let's talk a little bit of what is RoboCup. RoboCup is an international attempt to foster artificial intelligence and robotics in different socially significant domains. RoboCup was created in 1996 and it's managed by RoboCup Federation. Initially, its focus was to apply artificial intelligence and robotics for enable robots to play soccer and advance the field of robotics. Nowadays, it involves more than 40 countries and more than 3,000 participants that every year joins together for competing in different categories, in different socially significant domains. As I mentioned, RoboCup is comprised of various working groups dedicated to explore the application of artificial intelligence and robotics in different socially significant domains. Two examples of these domains are home assistance, where you apply robotics and artificial intelligence in order to enable or to facilitate the life of elderly people. The second area, this is an older one that involves the use of these technologies for industrial application, like logistics or even manufacturing. But the RoboCup Rescue Simulation Working Group was created a little bit after the establishment of the RoboCup itself. It was created in 1999 and it's focused on promoting research and development in the socially significant domain of natural disaster. The RoboCup Rescue Simulation Working Group promotes the use of artificial intelligence to support planning and decision-making of rescue teams in a post-disaster urban setting. Its mission is implemented through three different activities. The first one is to provide a simulator that can realistically simulate natural disaster and in order to enable this and support disaster response planning. The second type of activity is to evaluate benchmarks for response plans elaborated by policymakers to act in real natural disaster situations. And the last one is to organize competitions in order to put together and stimulate the interaction of researchers and practitioners that are working on the natural disaster domain. This presentation will concentrate mostly on the rescue simulator that is developed by this working group, and it's provided as an open source tool that can be applied for disaster response planning. So before we go, so the rescue simulator is a computer simulation platform that can realistically represent natural disaster scenarios. It can comprehensively represent all the situations that may happen in a natural disasters, so it can be used as a testbed for evaluating the effectiveness of rescue policies and strategies, and for defining new strategies for allocating resources. Before we can get into more details about these possible applications of the rescue simulator, let's try to understand a little bit the structure of the rescue simulator and its main features and components. The rescue simulator is composed of an environment that is usually represented by a map corresponding to a city like this one, Kobe, Japan. The city is represented with the roads and different buildings that will have different characteristics and materials that they are built of. These are the passive entities that exist in our environment. But the simulator also is composed of active entities, and these entities we call agents, and they are represented by this colored circle that I'm pointing here. So the green ones represent civilians, and the civilians are individuals that are victims of in a disaster. And they can be free, that they can go by themselves to the rescue shelter, or they can be trapped inside the buildings, or they can be trapped also in some blockades on the street. So these black signs here are the blockades that are preventing the civilians to navigate or go to the specific shelter. The blue ones are the police force, and the police force is responsible for unblocking the roads. So their main task is to clean up the roads in order to allow the other entities to navigate in the map more freely. Then we have the red ones, which are the fire brigades, and the fire brigades are responsible for unburying the civilians from collapsed buildings and release them for then the ambulances, which are the white circles, to load them and transport them to the shelters. So the police officer unblocks the roads, the fire brigades unbury the civilians, and the ambulances are responsible for transporting the civilians to the safe house or shelters. So all of these entities that I mentioned are active entities, and they have some characteristics that tries to reproduce or at least mimic the human characteristics or features. For instance, we have then in the simulator an environment, and on top of this environment we have these entities, software entities that are controllers of the each one of those active entities that I mentioned earlier. These entities, they can perceive the environment, so they have a range of perception that they can perceive the environment and what is going on in the environment, and they can then create some beliefs about the environment and about the other agents or about the other entities that exist in that environment. With that information of their beliefs, then they can make some decisions using some decision process mechanisms. These decision process mechanisms may be designed in different ways in order to represent different strategies that are designed by the planners. Once the agents decide what action to perform, they can actually act on this environment, and the actions can be proactive or reactive. Usually in this environment we have more reactive environment where the agent by perceiving some change in the environment reacts to that change by performing some action. In addition to all these features, these entities can also communicate among themselves. Since the perception has a range, a limited range, so the entities cannot observe the whole map, but just a region of the map where they are in. They can communicate one with the other in order to exchange information and about the different perspectives on the same environment. These different features allows us to design these different active entities that I already described earlier, but I will repeat here. So the ambulance teams that are responsible for transporting the civilians from one location into the shelter, the fire brigade, which is responsible for rescuing the civilians in a collapsed building, and the police force that is responsible for unblocking the roads, allowing the other entities to navigate on the map. And we have, of course, the civilians that may be represented as a green when they are healthy and a black when they are dead. So that there is a decrease in, there is different phases in intermediary here that indicates the decay in the health of the civilians. And that is what needs to be prevented by the fire brigade and ambulance when they unbury the civilians from debris and also transport them to a specific shelter. In addition to these active entities, we do also have several passive entities in addition to the roads and buildings. One of them is the ambulance center, another is the fire station, and the other is police office. These entities are related to different types of agents that we have, and they may be central where the decision-making process takes place instead of being done by each individual agent. And we have also a shelter, and this shelter represents a safe refuge where the civilians can be brought so they stop dying, they can take some treatment. Okay. With all these different types of with all these types of features and characteristics, we believe that this simulator is able to help in different types of post-disaster planning. For instance, we think that these simulators capable of supporting activities in the capacity planning and also in the exploration strategies. Of course, there's more possibilities and applications that we envision, but in this presentation, I will cover only those two possible applications. Let's get started with the planning. So the capacity planning, if you look at the INSARAG guidelines, you will see that they split the capacity planning in 4 phases. Phase 1 is the assessment of the community risks and rescue needs. Then phase 2, once you understand the community risks and the rescue needs, then you can elaborate a plan. And after the elaboration of the plan, you start training a team that will be able to support the planning and also develop some operational procedures that will guide the steps or the actions and tasks that the team will follow. But one problem that we face here is that, well, we don't know the effectiveness of this plan until some disaster happens. And we think that the rescue simulator can be useful in order to check or at least evaluate the effectiveness and efficiency of a planning that has been designed. In order to do this, we have a 4 steps process that we would like to propose. So we will start with initially the experts will design a response plan, and they will propose that for a specific region or for a specific event that may happen, right? Once you have these experts design the plan, we can then program that plan in the decision-making process of the different active entities that I mentioned earlier in the simulator. And we can also design the different scenarios where that may happen on that region. Once you finish the design of the different scenarios and also the embedding of the decision-making process on the different teams of agents or of entities that you may have in your simulator, you can then do several experiments by checking multiple situations. For instance, you can check the planning for if the planning is feasible and effective for a strong earthquake or a mild earthquake, and also in different times of the week. For instance, you check on the weekdays or weekends to see if there is anything that is is not effective in one of these situations. Even though although the weak or mild earthquake and a strong earthquake is very clear, the difference, the weekdays and weekends may not be so clear, because the weekdays and weekends, what we see is a distribution of the civilians in different parts of the city. For instance, in weekdays, the civilians during the day will be more concentrated in the business areas, while in the weekends, they will all scattered out throughout the city in their homes, so there may not be a concentration of civilians in one spot at one single time. Once you do all these experiments, then you will collect a lot of evaluation metrics that will be provided to the experts that design the response plan in order for them to evaluate the effectiveness of their own plan and propose some updates in order to improve the response plan in different situations. Okay? And by doing this, you can perform this process in an iterative process, in an iterative way multiple times until the experts are satisfied with the outcomes that they observe in all the different disaster scenarios that you experiment. Well, this is the first possibility of the use of the simulator. A second one is for the design of exploration strategies. If you look at the INSARAG guidelines again, they propose the sectorization of a disaster area in order to coordinate different teams for the exploration in a more more homogeneous way throughout the disaster area. So the sectorization is used in disaster situations to efficiently coordinate different teams in exploring more efficiently the affected area. However, there seems not to exist any specific method to perform the sectorization of the disaster area. Everything is based on personal experience. But here there is two main problems. You may not have this experienced personnel in place to help you to sectorize, or different experiences may lead to different types of sectorizations. In order to solve this kind of problem, or at least support a more formal and homogeneous sectorization of these environments, we propose the use of standardized artificial intelligence algorithms that are able to generate more consistent and balanced sectors. And here, by consistent and balanced, we mean that in all those sectors, the same amount of effort will be put by all the teams together. Once you have designed these sectors using some algorithm, then you can use the rescue simulator to evaluate the efficiency of the different sectorization for the exploration strategies. We can also compare the proposals from experts in the same environment and see which one would perform the best in this kind of situation, in different kinds of situations. This AI clustering also allows the generating of sectorization that adapts over time. So it is not something static that you perform at the beginning of the simulation or at the beginning of the disaster situation, but it's something that evolves over time depending on new activities or new tasks that are discovered. And finally, these different tasks may demand different sectorizations, like the police officers, which are responsible for cleaning up or unblocking the roads, and the ambulance and fire brigades, which are responsible to rescue civilians. They may have different needs for sectorizing or splitting the map and exploring the map. So you could use different algorithms or different sectorization strategies in order to explore and improve your rescue response in this case. So these were two main examples of how we can use the rescue simulator to evaluate different strategies or different plans in a real scenario, in order to support real teams. And if now we can here see that we have two different exploration strategies. The first one using one type of AI or artificial intelligence algorithm, and a second one using a different algorithm. You see that the outcomes from both or the sectorization are different, and you could see or check using the simulator which one would provide you the best outcome in the end. Okay, so those are two examples, as I mentioned. If you have any question, please feel free to send an email to one of those emails that I showed you at the beginning of the presentation, and we'll be happy to reply and give you more details about the simulator and also about the possible applications that we envision for this kind of tool. Thank you very much for your attention. I hope you enjoyed, and bye bye.